This is going to be part 5 to the section 4.2/4.3 series. And in this video, I'll do an example of applying Riemann sum and then an example of finding the exact area. When you're finding the exact area, pretty much you're going to be finding a Riemann sum, and then after you find the Riemann sum, you take the limit as n goes to infinity. So it's going to be sort of applying Riemann sum again, but just applying a limit at the very end. I didn't mention, well, I have mentioned this before, but if a function is increasing the right endpoints overshoot the area, and then if the left endpoints undershoot the area. Whereas if a function is decreasing, the right endpoints undershoot and the left endpoints overshoot. So it's opposite from that if for decreasing than that of increasing. And what I didn't talk about was an upper sum and lower sum, which essentially I just kind of drew these sort of picture to represent an upper sum and lower sum. And for the upper sum, I'm using the right endpoints of each subinterval. So I broke it up in this different subintervals, and then I'm choosing the right endpoint of that to form my heights of the rectangles. And then if you notice, there's I overshoot the area. My function's increasing, so f is increasing. All right, and that's using the right endpoints for an increasing function gives you what's called an upper sum. And this portion where I'm overshooting, that's like the error. All right, now for the lower sum, it's using, in this case, the left endpoints, and I'm undershooting. And again, our same function f is increasing. And I'm using left endpoints. So maybe I should write that also. So using left endpoints of the subintervals, whereas when for the upper sum, we're using the right endpoints. So I'm undershooting the area, and this is a lower sum, and you have these gaps. And then so I kind of didn't draw this very great, but you're going to have these gaps when you're undershooting, and that's the error. All right, then I drew a case when the function is decreasing. And for decreasing, great, it's the opposite. In this case, I'm using the right endpoints, but the right endpoints give me a lower sum. All right, so my lower sum undershoots, and again, I have those gaps in between here. That's the error involved. In the other case, in the function's decreasing, and we have an upper sum. And in this case, we're using the left endpoints of each subinterval. And you know the area that we're overshooting these, that's the error. All right, so the point is it's for an upper sum. If your function's increasing, you get the upper sum using the right endpoints, and then you get the lower sum using the left endpoints. And then it's opposite for the function when it's decreasing. So for decreasing, it's the right endpoints and then up for the lower sum, and then upper sum is using the left endpoints for decreasing. Now, as n goes to infinity, as you increase the number of rectangles to infinite amount of rectangles, that error shrinks to 0. All right, so I didn't mention lower sum and upper sum, but that in a nutshell, real quick, before I go into the example, is what lower sum and upper sum is, and it really depends on is the function increasing or decreasing as far as whether you use the right endpoints or left endpoints. And as n goes to infinity, the error shrinks to 0, so those gaps pretty much enclose down to where you get the actual area. All right, so number 41, this is an example from section 4.2. I'm going to find the lower and upper sums, and I'm going to leave my answer in terms of n, where n is the number of rectangles. And so our example is f of x equal to 3x, and it's on the closed interval 0 to 4. All right, so I'm going to consider n as an arbitrary number of rectangles, whereas previous example, in previous video, we did like a fixed number of rectangles, which was like 4. And I'm going to actually make use of the Riemann Sum Formula. So I went ahead and wrote down the Riemann Sum Formula, and I wrote down generally you have the left endpoints and right endpoints, and what you use for that, for the CI values. And when you're finding this Riemann sum, it's going to incorporate one or two of these summation formulas. So I went ahead and wrote down this, and this was theorem 4.2, and I discussed it in the previous video as well. All right, so these two things have boxed. I'm going to apply to the problem, and we're finding lower sum and upper sum. So solution. Well, we know f of x equal to 3x, that's going to be a line, and it's increasing because the slope is positive, right? Because the slope's 3. Well, if it's increasing, then I know for the lower sum or upper sum, right, the right endpoints overshoot. The right endpoints give me the upper sum if it's increasing, and the left endpoints give me the lower sum. So I need to find, well, is it increasing or decreasing? So if it is increasing, then the right endpoints I give the upper sum, and then left endpoints give the lower sum. And usually I've been using right endpoints for this Riemann sum formula, and that's because it's just easier to use the right endpoints. So I'm going to abbreviate upper sum. Since we're using n amount of rectangles, I'm going to abbreviate it as u parentheses n, so u for upper, and then capital L, and then parentheses n for lower sum. So I know I got to use the right endpoints for the upper sum, so I'll first do that case. And for my general formula, the right endpoints for a Riemann sum, where Ci is equal to a plus I times delta x. All right, our function is f of x equal to 3x, and we're on the interval 0 to 4. So I find delta x by doing b minus a over n. So I take the right endpoint 4 minus 0, and then so b is 4, a is 0, and then divide it by n. So the width is 4 over n. So then I can get the right endpoints, and so delta x is 4 over n. I'll circle that because I'll be plugging that into the formula for the Riemann sum. So then the right endpoints where it's a plus I times delta x. A is 0, so we use 0 plus I times 4 over n. All right, so the right endpoints, I'll just write it as 4 over n times I. All right, so that's the right endpoints have this structure. And then I need to find in the Riemann sum formula where it says f of ci. So well, I know the function itself is f of x equal to 3 times x. So when you find f of ci, you're plugging in 4n times I, so that's f of 4 over n times I. And that's 3 times x, that'll be 3 times 4 over n times I, so that's 12 over n times I is what f of ci is. All right, so now I have all the components I can use. So I'm plugging what I circled in yellow into the Riemann sum formula. All right, and we're doing the upper sum, right? So again, the function is 3 times x, that's an increasing function. And since it's increasing function, I use the right endpoints of the subintervals to get the upper sum. So that's what I'm finding now. So for upper sum, capital UN, so I'm just going to plug into the Riemann sum. So f of ci, we got that to be 12 over n times I. All right, that's the f of ci part. And then the delta x, we got that to be 4 over n. And then it's a matter of just finding this sum. All right, well, I would do 12 times 4, that's 48. And then n times n is n squared, so this is the sum. I equals 1 to n, 48 over n squared times I. And then you can factor out the 48 over n squared in front of the summation so that the summation only involves I. And the reason we're doing that is so that we can make use of these summation formulas. In this case, we're going to make use of this one. So factor it out. So that's going to be 48 over n squared times the summation of I. Oh, I don't know why I put I squared. And then we plug in the formula, and that's from theorem 4.2. And that's what I plug in for the summation of I. This will equal 48 over n squared times, and then I'll put a different color for this, n times n plus 1 divided by 2. And then I try to simplify it. Well, I can do n squared, I can cancel out n from n squared. That makes just 48 over n. And then I could do 48 divided by 2. That's 24. So then I have 24 over n times n plus 1. Right, because we got rid of the 2 when we divided 48 by 2. And then the n went away next to the n plus 1 because of n divided by n squared. Then from here, I just distribute 24 over n times n, and then 24 over n times 1. So when I do 24 over n times n, the n's cancel out, so you get 24. And then plus, and then 24 over n times 1, that's 24 over n. All right, that's what the upper sum is in terms of n rectangles. So I'll box that. That's what we need for part of the question, is finding the upper sum. Now I'm going to find the lower sum. All right, so for the upper sum, I use the right endpoints, and again, that's because the function's increasing. The lower sum, I'm going to use the left endpoints. And the left endpoints are given by ci is equal to a plus I minus 1 times delta x. Now I'll just write the function over again. It's f of x equal to 3x, and we're on interval 0 to 4. We found delta x. That was 4 over n. Okay, that's our width. And just plugging that in, and plugging a is 0 into ci, so that's going to be ci is equal to 0 plus I minus 1 times 4 over n. All right, and I'm going to actually just write it as just how you see it. I minus 1 times 4 over n. Now I plug that in to f. I need to find f of ci, and that's plugging I minus 1 times 4 over n. I plug that in for x. So for f of ci, where it's going to be equal to 3 times x, is 3 times this whole thing. So 3 times I minus 1 over, and then times 4 over n. In other words, I just do 3 times 4 is 12. So f of ci be 12 over n. And then I'll write I minus 1 like that. That's just a preference thing. I like to put the I stuff after. So I did 3 times 4 is 12, so that's 12 over n times I minus 1. All right, so I plug both of these into the Riemann sum. In this case, we're dealing with the lower sum. So I'm calling the lower sum L of n. And then I'll just write down generally what Riemann sum formula is. All right, so that's the Riemann sum formula. My f of ci, that's the 12 over n times I minus 1. And then my delta x, I'm supposed to use a different color. Delta x was 4 over n. All right, so then it's pretty similar as last time. So I do 12 times 4 is 48. Then I have 48 over n squared. It's just now I have I minus 1 versus last time I had just I. So this will equal the summation, I equals 1 to n, and it's 48 over n squared times I minus 1. All right, so it's, I guess, a little bit more complicated with the because I have I minus 1 versus just I, but I'll still factor out the 48 over n squared. All right, so I can't just bring out -1 since I have I minus 1 as one kind of factor. Now what I can do is use some summation rules. So I'll use the following. I have a minus b, summation of that. You can break that up as the summation of a minus the summation of b. So in this case, and I still have the 48 over n squared, but then I'm going to do in brackets, I apply this. So it's going to be the summation of I minus the summation of 1. All right, so I broke it up into two summations and make sure to multiply 48 over n squared to that whole thing. Now I'm going to use the summation formulas. Well, I have the summation of I. That's n times n plus 1 divided by 2. So that's what I'll apply for that one. And then the other one of the summation formulas, if you sum up C, you get C times n. And in this case, C is 1. So that'll be 1 times n, which is n. All right, so this will equal so summation of I, that's n times n plus 1 divided by 2. And then minus summation of 1, so in this case C is 1, so that'll be 1 times n, which is n. So that'll be minus n. All right, so hopefully that makes sense. I just applied these two formulas, and in this case for 1 was in place of C, and it's always C times the top index, and so 1 times n, which is n. Now what I'm going to do now is just combine into one fraction. So I'm going to focus on the parentheses, what's in brackets or parentheses. I'm going to combine to one fraction. All right, and I'll do that right here. So if I have minus n, you can write that as minus n over 1. I want the same to denominator of 2, so I multiply top and bottom by 2. I do 2 times that, top and bottom, and that'll give me the one fraction where I have n times n plus 1 minus 2n, all of that divided by 2. All right, that's what it is as one fraction. So I had to change n so that it becomes 2n over 2, so that they have the same denominator. All right, so that gives me 48 over n squared. And then in brackets is the n times n plus 1 minus 2n over 2. And then I try to see if I can do some simplification. Well, I can do, let's see. 48 divided by 2 is 24, so I can do that. And let's see, so I have an n times n plus 1 and then minus 2n. Both of those share n in common, so I could factor out an n and then cancel out an n from the n squared. So in other words, I can go ahead and cancel out the 2 for the exponent, so I just have n, while simultaneously canceling out these n's, since I'll be factoring out an n up top, and then dividing that with an n from the n squared. So that gives me 24 over n, and I got rid of the n, and then so it's just n plus 1, and then minus 2. All right, and all I do now is just distribute, and I guess I could go ahead and just do 1 minus 2, which is negative 1. All right, now I'll distribute 24 over n. So I just combined these two. All right, so distribute. So 24 over n times n is 24, because the n's cancel out. And then minus 24 over n. And that's the lower sum. All right, so in conclusion, you'll see that the upper sum and lower sum look very similar. Upper sum was 24 plus 24 over n, and the lower sum is 24 minus 24 over n. So one of them has plus 24 over n, one of them has minus 24 over n. That's the error involved. So lower sum. And that's all they wanted in that question, was the upper sum and lower sum. So we'll make a comment. If they ask for the exact area, the exact area is found by just taking the limit as n goes to infinity. And notice that the upper sum and lower sum will still give you the same limit. Of 24. All right, because as n goes to infinity, 24 over n shrinks to 0. So then the upper sum, which we know is 24 plus 24 over n, if I take the limit as n goes to infinity, this goes to 24 plus 0, which is 24. And then lower sum, same thing, it's just 24 minus 0. All right, now they give you the same limit, and that's going to be true when you take, so finding the exact area. I guess the point I'm trying to make is when you're asked to find the exact area, it doesn't matter if you use the upper sum or lower sum. And I generally just go with the one that has CI being the right endpoints. And it just happened that since our function was increasing in this example, our right endpoints gave us the upper sum. All right, so I always use the right endpoints because this was quicker or less work than when we did the left endpoints because I had I minus 1. That was more work. So I just go with whichever one uses the right endpoints. Since it's, to me, less work. So less algebra. All right, so that leads me into the next problem. The next problem is going to actually be finding the exact area. This one I just added this as a comment, is that the lower sum and upper sum both give you 24 if you take the limit as n goes to infinity. And that's all it is. For exact area, you find that Riemann sum, and then you take the limit. So this example I'm about to do is actually going to be one where they explicitly ask find the exact area. So this is number 47 from section 4.2. So we're going to find the area by applying the limit definition. And our function's f of x equal to negative 4x plus 5. And it's on the interval 0 to 1. All right, so the limit definition is pretty much just the same as what we were doing. It's just finding the Riemann sum and then taking the limit as n goes to infinity. So limit definition, so area equals the limit, n goes to infinity, and then it's the Riemann sum. And then delta x is b minus a over n, and then ci can be anything you choose. I choose the right endpoints, a plus I times delta x. So this is using right endpoints, but again, I just showed that it doesn't matter if you use the right or left endpoints. As long as n goes to infinity, it gives you the same area. All right, so what I'm going to do first, find the Riemann sum. And then apply the limit as n goes to infinity at the end. All right, so this first step's the same as what we were doing in the previous example. So delta x is b minus a over n. Well, in our case, our interval is 0 to 1, so let me rewrite the function. Delta x, 1 minus 0 over n, so that's 1 over n. That's our width. That's what I plug in. Then using the right endpoints, a plus I times delta x. So ci is going to equal 0 plus I times 1 over n. So that's just, you can think of that as just I over n, or 1 over n times I. I'll just write it as 1 over n times I. And then I plug that in to the function. To get f of ci. So f of ci, so where x is, I'm plugging in 1 over n times I. All right, so negative 4 over n times I plus 5. All right, that's what I'll plug into the Riemann sum. All right, so what it's going to turn into for the Riemann sum all right, so the f of ci, that's the negative 4 over n times I plus 5. And then times delta x is 1 over n. All right, so now it's a matter of trying to simplify this, this beast. So what I'll do is I'll factor out the 1 over n in front of the summation. So then I'll break this up into two summations, because I know for, like how I did previously, if I have summation of a plus b, I can change that to be the summation of a plus the summation of b. So I'm going to break this up. So it's a summation of negative 4 over n, and then I, and then plus summation of 5. And all of that's being multiplied by 1 over n. So then for the first summation, I could factor out negative 4 over n. That way I just have the summation of I. And I could apply a formula. Now for the summation of 5, from theorem 4.2, if you have summation of c, that becomes c times n. In this case, 5 is c, so that becomes 5 times n. All right, that's what I used for that part. And then for the summation of I, that's n times n plus 1 divided by 2 from the same theorem. So I have 1 over n, and then in brackets, negative 4 over n, and then times n plus 1 over 2, and then I still have the plus 5n. All right, so now I try to simplify this as much as I can, and what I can do is I can do negative 4 divided by 2. I start inside the brackets. So I do negative 4 divided by 2. That's negative 2. And then I can divide out n with n right there. So that leaves me with, so the n divides out, so I have just negative 2, and then times, and it's really just n plus 1. Since I divided out the 2 and the other n divided out because of the n's canceling, and then plus 5n. Then I just distribute negative 2. That's negative 2n minus 2 plus 5n. And I can just combine negative 2n with 5n to make 3n. So then I have 3n minus 2 in the brackets. All right, now I'll distribute 1 over n. So that's so 1 over n times 3, and the n's cancel out, so you're left with 3. And then 1 over n times minus 2, that's going to be minus 2 over n. All right, that's what we get for the Riemann sum. All right, so that's the first part. Now all we do is take the limit. Well, we know for the 2 over n part, that's going to go to 0. So as n at 2 over n shrinks to 0 as n goes to infinity. All right, that's dealing with our infinite limits, and that's a rational function. The top part is a constant. A constant has a degree of 0, and the denominator has n to the first power, so the degree on the denominator is 1, so the degree on the bottom is more than the degree up top. So as n goes to infinity, that goes to 0. All right, so now limit n goes to infinity of our Riemann sum. That's going to be 3 minus 0, which is going to give us 3. And that's going to be the exact area. All right, so the point is for finding exact area, you find the Riemann sum first, and then apply the limit as n goes to infinity. And for that Riemann sum, it's just a preference thing for what you use for CI, being right endpoints or left endpoints. I use right endpoints, it's easier, less algebra to deal with. All right, because as long as n goes to infinity, it doesn't matter what you use for CI, the summations, so whether I use upper sum or lower sum, go to the same value for the exact area. For the next video, I'm going to cover examples involving definite intervals. Which really is doing this limit definition.